Okay, now we want to talk about what happens during address translation, and this leads to a discussion of translation lookaside buffers. The addresses that the CPU generates are virtual addresses. They correspond to locations in virtual memory, but of course we need to refer to the physical memory locations where those addresses are located. So we have a page table, and the page table takes the virtual page number and tells us what is the physical page frame address where that memory is found at. But we can't afford to access the page table in every reference because that's too slow. So instead we use a translation lookaside buffer, or TLB, which is like a special cache that's indexed by page number. If you're accessing a page and there's a hit, that means the page is in main memory, um, then you immediately obtain the page frame address. But if there's no hit in the TLB, well, the page may still be in main memory. You just need to go out and look at the page table to see if it is actually in main memory. But that means doing it the long way. And sometimes actually that takes a very long time, and so diminishing that time is an area of active research, but we won't go into that much detail today. So what this means is that the TLB needs to be accessed before you know the physical address, and therefore before you can access the cache. So we translate the virtual address to a physical address through the TLB, then we access the cache. Either there's a cache hit, in which case the cache returns the contents of that location, or otherwise there's a cache miss, which means we go to memory. Well, this adds an extra cycle if there's a hit, because you got to do the address translation as well. So how can we avoid wasting this time? Let's look at what happens when a memory address is accessed. So I've got this diagram for you here. You see that there is a virtual address up at the top, and the virtual address is translated to a physical address. Um, if you actually, once you have the physical address, you have these three fields: tag, index, and offset. So the tag field is used to compare with all the tags that are in the right set of the cache. The index field is used to select which set you're looking in, and then the offset field determines where in that cache line you look to get the information. So the first thing you need to do is, well, I've got that question for you here. I've got 7 steps in cache access, and in this quiz I'd like you to reorganize them into the correct order. Okay, let's see. Well, we always need to read cache lines into the sense amplifiers, which is right over here. We take the lines, we read them into the set amplifiers, and then we select the word. So if we know the index before address translation takes place, we can perform some access of the cache while address translation is occurring. And this is a speed up between power and efficiency. If we wanted power to be most efficient, then which step there could we skip? Look at the steps that we've reorganized there and numbered 1 through 7 right above. For power efficiency, which step can sometimes be skipped? Well, that would be number 4, because we might not have to do that if none of the tags actually matches. But if we want to have maximum speed, then we'd rather perform steps in parallel. So which steps could be performed in parallel? Well, you can't do comparison until you pull down the tags, but you could pull down the tags at the same time that you read all lines in the set into the sense amplifiers. So the steps that you could perform in parallel is access the set, and then continue to pull down the tags, and then finally read the lines of the set into the sense amplifiers, and only then, after address translation completes, would you compare the tags with the tag of the sought after address.